We've started generalizing the Poisson process model class, and we can now model a huge array of natural phenomena. But despite this, there's one glaring issue with the machinery that we've developed up to now, and it's got to do with the rather restrictive assumptions under which we built the counting mechanism. Indeed, some of you may have immediately spotted the issue the moment I introduced the supposedly ideal metaphor of a marathon that we've been using throughout this series. So to see what I'm on about, consider one of the data tables I presented early on in the series, where we recorded the arrival times of runners up to the 3 hours and 30 minutes mark of the Marathon. You'll notice that there's something off about the first inter-arrival time. It seems large when compared to the other inter-arrival times. Now this indicates that the arrival rate must have been 0 or very small for some time, after which it must have changed and we then start observing arrivals. Okay, now this is at odds with the assumption that the rate parameter of the counting process is constant over any particular window of time. Indeed, under our model process, if we were to break up the time domain into sub-intervals or bins of equal length and count the frequencies of the arrival times in each of those bins, we'd expect to observe frequencies of similar magnitudes, since the inter-arrival times are IID exponential with the same rate parameter. The discrepancy between the magnitudes of the first inter-arrival and the subsequent inter-arrivals, i.e. observing nothing for well over 2 hours, after which we then seemingly observe regular arrivals, clearly indicates a departure of our model assumptions from the behavior of the true data generating process, i.e. the thing that we're modeling. In fact, it's not just the first inter-arrival time that's troubling if we were to take a closer look at the data. Now, consider, for example, another timesheet, this time taken from the 2020 Cape Peninsula Marathon. Now, I've pivoted to this data set because the data were easier to source and parse, but the dynamics are similar to what we would observe for other marathons. Now, here we record finish times in minutes for all participants, and then we summarize the data as follows. Let's break up the time domain into sub-intervals of length 10 minutes over a total observation window of 400 minutes. And then we calculate the frequencies of the arrival times in each of those sub-intervals as the arrivals are observed. Now initially we observe no arrivals, and this continues for about 2 hours and 20 minutes. Then we start to observe runners arrive. Only a few initially, but then the frequencies start to increase sharply up to almost the 5-hour mark, after which it then subsides again back to 0. And all of this makes sense, right? We should expect not to see any runners for at least the first 2 hours, right? The world record is just over 2 hours. And that's a consequence of the physical limitations of the human body. Furthermore, running pace is obviously stratified by physiological and treatment factors such as body composition and training regimes. So one should expect that running times are stratified as well. And in an ensemble of various strata, like this, it should be at the very least skewly distributed, but over a finite support, since we would actually have a cutoff time for the marathon as well. Okay, sure. Perfect metaphor out the window, right? Well, it looks like there are in fact a number of rather fundamental features that we've blindly omitted from our mathematical model, at least where modeling running timesheets are concerned. Clearly, the rate at which arrivals occur for such a process varies with time, and our machinery is predicated on a constant arrival rate. Well, as it happens, we can still salvage the machinery by relaxing the assumptions under which we built the class, specifically that of time homogeneity. Indeed, although it's often underemphasized in undergraduate contexts, since the mathematics becomes messy or intractable rather quickly, virtually all real-world processes exhibit some explicitly time-dependent dynamical behavior, and thus we will modify our mathematical machinery accordingly. So for today's lecture, we'll cover time-inhomogeneous Poisson processes, derive some useful statistical results under this generalization, and then cover a quick example application. So let's jump in. Cool, so we start from the ground up with the Poisson postulates. So, following Ross et al. Again, a counting process, NT, t is greater than or equal to naught, is a non-stationary, non-homogeneous, or time-inhomogeneous Poisson process. You may use any of those names, we will be using time-inhomogeneous Poisson process to make it explicit, with intensity function lambda t greater than or equal to naught. So note that the rate parameter lambda here is now a function, so lambda t, if 1, n naught equals naught. So counting again starts from 0. 2, the process has independent increments. Now they need not be stationary. Okay, so we drop the assumption of stationarity that we had before. 3, the probability of observing exactly one event over a small interval of time, length h, is lambda t times h. Okay, so note previously we had lambda, where lambda was a constant, now it's a function lambda t, so at that point lim t. So lambda t times h plus terms which are little o h, and the meaning of little o h has not changed. 4, the probability of observing 2 or more events in an interval of length h is just going to be little o h. Okay, so those give us the Poisson postulates for the time-inhomogeneous case of the Poisson process. And indeed, we relax the assumption of stationarity of the increments, but now we need to take care in how we apply the calculus, since the distribution of the increments explicitly depends on where the process is in time. As such, we will henceforth adopt the concept of a reference point again, so S, somewhere in the time domain, as the starting point of an arbitrary interval for any subsequent probability calculus. Now, as before, these postulates lead us to the central result for time-inhomogeneous Poisson processes, and the theorem in question is as follows. Let mt, so some function mt, denote the so-called mean value function, which is defined as the integral running from 0 to t over lambda du du. Then for a time-inhomogeneous Poisson process, nt, such as t is greater than or equal to naught, we will have that the probability that the count equals n in some time window running from s to s plus t is just Poisson distributed with mean ms plus t minus ms. So the mean value function evaluated at s plus t minus the mean value function evaluated at s. And this holds for all n greater than or equal to naught. And obviously, because that distribution is Poisson, we will again have the result that, well, the expectation of the count over that time window from s to s plus t, so the expectation of ns plus t minus ns, is just ms plus t minus ms. Okay, and the variance will equal to mean because it's Poisson, and again, it's just ms plus t minus ms. Okay, now note here that the distribution of the increment now depends both on the length of the transition horizon and where it is in time. Previously, we had that it didn't really matter where it was in time, it only mattered how long that interval is. But now it explicitly depends on both how long that interval is and where it is in time. Okay, and that concludes the main result pertaining to the state variable of a time-inhomogeneous Poisson process. Now we again have that the state variable is Poisson, but now with a rate parameter which is determined by the mean value function, and hence its name. Cool, so let's quickly explore the relationship between the intensity function and the mean value function. Okay, so the rate parameter of the process can now be thought of as a function of time, and it is useful to draw a quick figure relating the mean value function to its parameter. So for example, let's take lambda t equals 2 plus sine 2 pi t. Okay, and we'll say that that is the intensity over some time window running from 0 to 1. So for t, all t in 0 to 1. Well, then we'll have that the mean value function, okay, mt, well, that's just going to be the antiderivative of that expression. So 2u minus cosine 2 pi u divided by 2 pi, evaluated at the endpoints t and 0 and subtracted, which gives us the mean value function. Now, though it is the shape of the intensity function that we visualized, it is useful to think of lambda t, so the intensity function, as an instantaneous rate of the process at any point in time, hence intensity, and the mean value function as integrating information about the trajectory of the intensity function over its history up to time t. Indeed, this interpretation will be useful later on when we generalize by allowing the intensity function to be a stochastic process itself. Now, Just a quick refresher on some calculus here, since I often observe some confusion when students need to prepare responses where the calculation of the mean value function is concerned. So what I've done is I've taken the fundamental theorem of calculus, as communicated in the ubiquitous calculus text by James Stewart, and I've adapted the notation to reflect the relationship between the intensity function and the mean value function. And it goes as follows. So this is adapted from Stewart. Suppose lambda is continuous on a interval a to b, a being inclusive. If some function mt is defined as the integral from a to t of lambda u du for t on interval a to b inclusive, then, well, m prime t, so the first derivative of m prime t, is just lambda t. Okay, so the intensity function evaluated at t, and we can think of m now here as being the mean value function. Also, if we evaluate the definite integral, so the integral of the integral running from a to b of lambda u du, well, then that's just m evaluated at b minus m evaluated at a. Okay, and we may use the sort of block parenthetical notation where we say, okay, let m, say, at argument v be the antiderivative of lambda u, then we can just evaluate that at the endpoints b and a, subtract them to assign a value to the definite integral. Okay, and this holds where m is any antiderivative of lambda, so m prime equals lambda. Okay, so that's the fundamental theorem of calculus, and the main source of the confusion that I'm hoping to clear up here is with the use of t in particular. So you'll see that wherever I write integrals, I use u for the argument of the integrand, and v for the argument of an antiderivative, which is to be evaluated at the endpoints of an interval and then difference to assign a value to the definite integral. I only ever use t for the argument where the intensity function or mean value function is presented explicitly as a function. So only after I've done any integration will it show up as an argument to the mean value function, for example. Now, more often than not, you'll just be evaluating definite integrals, but if I ever ask you for a function, it can easily go wrong. Okay, now this might seem obvious, but often under time pressure and in exams, students use t for both the integrand and the limit, or some other minor mistake like that, which ends up costing marks unnecessarily. Now, we're all human, it happens, and I know this because I've done this as well. But if you use the above convention, you'll minimize the probability of making a mistake. Cool, so let's quickly outline the central statement that the increments are Poisson with parameter ms plus t minus ms, where m is the mean value function. Now, I won't go into too much detail, as it follows very much the same steps as the proof we had for the time-homogeneous case, but in any case, here goes. Okay, so for the proof, we will again define a shorthand notation, so this time we'll just have an additional argument. Okay, and the shorthand goes as p sub n st is just the probability of ns plus t minus ns equals n. Okay, so the probability that the count is n over an interval running from s to s plus t, where s is now a sort of start of the interval or reference point, if you like, and t is the amount of time elapsed since the start of that interval. Okay, now our proof again starts with the simple case where we look at, well, what if the count is 0? Okay, and how we find an expression for that is again by finding a differential equation for that probability, solving it, and then noting, okay, well, that is a probability from the relevant distribution that we have. Okay, so how do we show that? Well, let's start with the probability that the count is 0 over an interval running from s to s plus t plus h. So using our shorthand notation, p naught s t plus h, which is just the probability of ns plus t plus h minus ns equals naught. That's from our definition. Well, what we're going to do is the same as before. We're going to take that interval, we're going to break it up into two parts. One running from s to s plus t, the other one running from s plus t to s plus t plus h. So a short little interval at the end. And because we say that the count over that entire interval must be 0, well, it must be 0 in both of these sub-intervals into which we broke it up. Okay, so write that as a joint probability. Well, because those increments are independent, so note that the independence of the increments are still in our postulates for the time-inhomogeneous case. We can write that as the product of two probabilities, okay, which are just p naught s plus t for length h times p naught s t. Okay, so an interval of length t. Now, from our postulates, which concerns little intervals of length h, we can now just plug in the relevant expressions there, right? So we evaluate p naught s plus t, h, as 1 minus lambda s plus t times h, plus terms which are little o h. All of that in brackets multiplied by p naught s t. Okay, so note again, that's just our Poisson postulates at play, and the relevant point in time is s plus t. So that's the point at which we broke up that interval. Cool. Now, we can take this expression, we can rearrange it, divide by h, and take limits to arrive at a differential equation. And we will find that the relevant ordinary differential equation is going to be the log of the probability of observing a count of 0 in an interval starting at time s of length t, so s to s plus t, is just minus the integral running from 0 to t of lambda s plus u du plus some constant. Okay. Now we can do some manipulative math, and then we can say, well, that just probability just evaluates to p naught st is just some constant k times e to the minus ms plus t minus ms, okay, where m is the mean value function as we defined it before. Okay, so this is where we finally see the mean value function come in. It's from that integral. Okay, and then we can just again substitute the boundary condition. Well, that zero count in 0 time occurs almost surely, so that yields that that constant must be 1. So the relevant probability, p naught st, is just e to the minus ms plus t minus ms. Okay, cool. And we will see that, okay, that does actually map to our Poisson distribution. Awesome. Right, so we've got 2 more steps to go, and I'll just quickly outline them. Okay, so step 2, as you remember, concerns finding a system of ordinary differential equations for the general case, right, where n is not just naught. Okay, and what we can do is we can take again that interval running from s to s plus t plus h. We can again break it up into 2 intervals around s plus t. Then we can say, well, okay, for the general case where n is not 0, how can it be distributed across those 2 intervals? And then we plug in our postulates. We rearrange, divide by h, take the limits, and then we end at a nice, neat differential equation, which says that the first derivative with respect to t of pn arguments st, okay, so note that we're differentiating with respect to t still, s is just the reference point, is just minus lambda s plus t, okay, times p sub n arguments st plus lambda s plus t times p sub n arguments n minus 1 arguments s plus t. And this equation will hold for all n running from 1, 2, 3, all the way up to infinity. Okay. And this equation, together with step 1, yields a system of differential equations, or ordinary differential equations, albeit infinite system, which we can solve for all n, or which we can use to find an ordinary differential equation for the generating function as we did before. Now, albeit over the interval s to s plus t, rather than 0 to t, like we did before. And indeed, we do our manipulative mathematics as we did before, and then we arrive at step 3, where we find the ordinary differential equation for the generating function, which we will denote g here. And note again, it will have an additional argument here. So gzst denotes the generating function, where z is the dummy variable, s is the start of an interval, and t is the length of the interval again. Okay, and we'll find that the first derivative of the generating function is just equal to lambda s plus t times z minus 1, where z is the dummy variable, times gzst. And again, plugging in the boundary condition that a count of 0 occurs certainly over an interval of length 0, we can see that, well, if we solve this equation, we end up with an expression for the generating function, gzst, as the exponent of z minus 1 times the integral running from 0 to t of lambda s plus u du. Okay, so we write out that integral, manipulate it a bit, and then we see that, okay, let's reevaluate that as the exponent of z minus 1 times ms plus t minus ms, where m is the definition of the mean value function. Cool. And there you have it. So, ns plus t minus ns is Poisson with parameter ms plus t minus ms by the uniqueness of the generating function. And that concludes the proof. Now, I suggest you go through the proof with the one for the homogeneous case, just for reference. I know it looks messy, but you'll see that apart from the integrals and keeping track of the relevant subintervals, it's pretty much the same burger. Okay, again, the only trick here is noting, well, what are the start and end points of the subintervals, and to keep in mind that it's s to t, and then, or s to s plus t, and then s plus t to s plus t plus h. Okay, those are the relevant intervals, and then you just need to keep track of the integrals. Cool, so let's look at a quick example problem. Let's revisit the 2020 Imola Marathon, but now suppose we revise our model for counting runners who cross the finish line between the 180 to 210 minute marks as follows. Okay, so we use a time-inhomogeneous Poisson process, and we let t denote the time elapsed after 180 minutes, and then set the intensity function measured in minutes as follows. So lambda t is defined as some polynomial for t running from 0 to 10, it's another polynomial for t running from 10 to 20, and then yet another polynomial for t running from 20 to 30. Okay, so what's strange about this? Well, we've got an intensity function which is piecewise defined over 10-minute subintervals of the time window over which our questions pertain. Okay, and then we've got a bunch of questions. So question 1 is, how many runners are expected to finish between 185 minutes and 210 minutes? And then 2, what is the probability of observing at least 2 runners finish between the 180 and 185 minute marks? Okay, cool. So again, we're modeling this using now a time-inhomogeneous Poisson process. We've got a definition for the intensity function, and then we have a result, right? What is the main result for time-inhomogeneous Poisson processes? Well, if we have the intensity function, we know that the count is distributed Poisson with parameter given by the mean value function evaluated at the relevant endpoints. Okay, now again, we have this issue that we've got a piecewise defined intensity function. Okay, and as you will see, with our first question, we now have to integrate over a particular range which spans the subintervals over which it's defined. Okay, so let's tackle question 1. How many runners are expected to finish between 185 minutes and 210 minutes? Okay, now if we see that t is defined for as the time after the 180th minute, so that means we need to integrate for t running from 5 to 30. Okay, now is that a problem? Well, no, lambda is piecewise defined, but if we calculate the integral for that, that just means calculating the integrals over the subintervals, making sure that obviously we're still within the relevant time window, and then adding them up together. Okay, so the way we actually answer this question is by sort of, again, doing things piecewise, integrating piecewise, and the best way to do that is with a table. So the way I do this is I always set up a table. The first column, okay, I'll have the relevant subintervals over which we integrate, so s to s plus t. I then write down the intensity function using the argument u, again, as I've mentioned before, just a convention. Then it's antiderivative m at argument v, again, another convention of mine. And then I evaluate that mv, so in our final column, at the endpoints and subtract them to assign a value to the integral for the relevant subinterval. Okay, and where are these subintervals? Well, we put these subintervals on the rows of our table. And then right at the end, if our time window spans most of those any of those subintervals, we just add them together to get the value of the integral over all of those subintervals. Okay, and indeed, from the question, we see, okay, that runs from 185 minutes to 210 minutes, so that's t running from 5 to 30. Okay, so in the first subinterval, we need to integrate from 5 to 10. Okay, so we're filling in the elements in our first column. Second interval, 10 to 20. Third interval, 20 to 30. Okay, well, what is lambda u over those intervals? Okay, the intensity. Okay, for all of the points between 5 and 10, it's going to be a half plus 1 over 20 u. For all of the points between 10 and 20, it's going to be 1 over 40 u squared plus 1 over 20 u minus 2. Okay, and then finally for the third interval at all of those points, it's just going to be 11 minus 1 over 200 u squared. Cool. Next, we need to evaluate the integrals for those. Okay, so for the first expression, it's going to be a half v. So note, I'm switching to the argument v here. So a half v plus 1 over 40v squared. For the second expression, it's going to be 1 over 120v cubed plus 1 over 40v squared minus 2v. And then finally 11v minus 1 over 600v cubed for the final interval. Cool. So we've got the expressions, and now we get to our calculation. Evaluate it at the endpoint, subtract those values, and then we'll see, well, that the expectation, or the contribution to the expectation of the first subinterval is going to be 4.375. Contribution of the second subinterval is going to be 45.83 recurring. The contribution of the final interval is going to be 78.3 recurring. And then again, because we're integrating over a window which spans all those subintervals, we just add them together, add them up, and we'll find that the expectation or the mean value function evaluated at those endpoints subtracted is going to be 128.542 roughly. Okay, so does that help us answer our question? The question asked how many runners are expected to finish between 185 and 210 minutes. Well, under this model, we go and calculate, and we see that it's about 129 runners that we expect to finish. Okay, cool. So, piecewise defined intensity function, not a problem. Question B. What is the probability of observing at least 2 runners finish between the 180 and 185 minutes mark? Okay, so now this is the other bit of the interval that we didn't look at earlier. Now again, we can just do this in table form. We look at our intensity function. We note that we need to integrate for t running from 0 to 5. Okay, so it's piecewise defined. Okay, the only relevant interval is the first subinterval. So we integrate that expression. It's going to be a half v plus 1 over 40v squared. Evaluate that at the endpoints and subtract, and we get, well, that value is going to be 3.125. What does that give us? Well, that gives us the mean over that interval, but we also know that, well, over that interval it's going to be Poisson distributed with that parameter, and the question asks about a probability. We can evaluate that probability of observing at least 2 runners as 1 minus the probability of observing exactly 0 or 1 runners in that time window. So 1 minus P005 minus P105. Okay, calculate those values, plug it into our expression, and then we get the probability 0.82 roughly. Okay, so it's a likely event, but yeah, it turns out the calculation isn't that bad. Okay, and that concludes our example problem. Cool, so that's that for now. I hope you found that interesting. If there's anything that you should take away from today's lecture, it should be that you should always check the validity of strong assumptions such as time homogeneity. Indeed, whatever the application is that you have in mind, relaxing that assumption will almost surely make your life more difficult, both computationally and analytically. But any subsequent inference or interpretation you do will be dependent on how realistic your model is in the first place. So it will almost surely actually pay off in the end to do the hard work and get it working under those relaxed assumptions. In any case, ignorance of that fact might actually cost you more than just computational analytical time. So with that, I'll leave up some problems for you to check out, and then I'll see you in the next one.